Good afternoon. Hello, everyone. Thank you very much. Thank you for joining the Rail Baltica Academy. My name is Andrejs Mislēvičs, and I'm a signaling and communications team leader at AB Rail. And for today, our session will introduce you to the basics of control command and signaling subsystems. First of all, I would like to introduce myself. I'm originally coming from Riga, and I graduated from Riga Technical University, and afterwards continued my education in the field of control, command and signaling in Germany. And from my work experience, I would mention participation in involvement in many international projects, and most significant of them were ETCS project in Germany on the high-speed line Nuremberg-Erfurt-Halle, Leipzig-Berlin, and new high-speed railway line project for the line Stuttgart-Ulm. Considering our today's contents for this session, I propose the following structure: that we start with an introduction where I will explain you the context of the railway systems and where does the control command and signaling, or CCS, finds itself in this system. And afterwards, I would explain you subsystems of CCS, namely interlocking and traffic management, signaling and train protection, then Ertms as a specific train protection system. And then I will briefly explain you ancillary systems or supporting systems. And afterwards, we will have a question and answer session. And I will answer the questions which you would put in writing in the chat. So this is the plan. Yes, welcome on board, and let's start with the introduction. If we look at railway as a system, we see that it consists of three parts. So the first part is vehicle, traction units, wagons, locomotives. The second part is driveway, so infrastructure which allows train to go. This is structures, earthworks, and of course rails, switches, catenary system, and stations and platforms. So this is the second part. And the third part is the control command and signaling, which we will discuss today in very detail. And this consists of interlocking and traffic management, signaling and train protection, and supporting systems. And it is important that all these three parts are interacting. So vehicle, driveway, and CCS, and these are a prerequisite for railway operations. And on the right side, you see that for operations, all three parts are needed, and in our today's session, we will look on the part which is called CCS. If we look at the railway as the transport system, so we notice that there are two significant characteristics. First one is that the driveway is given by the track system, by rails, and the driveway could be selected in two directions only on movable elements, which are called switches or turnouts. Thus, the driveway shall be set in advance by placing switches in right positions. This is called direction control. And on the picture on the right side, you see that these two switches are set in the positions indicated by arrows, thus allowing the train movement only in these positions, in these directions. And the second characteristic is relatively low braking capabilities because of interaction of a steel wheel and a steel rail, and relatively high speeds. For example, RB rail line design speed will be 249 kilometers per hour, and as well very high masses lead to long braking distances. So, for example, if the train has a speed of 40-70 kilometers per hour, it is no longer possible for the train driver to to control all the driveway. Therefore, in case of higher speeds, the train driver shall get information on track vacancy by other means. And this function is fulfilled by track side signals, as is indicated on the picture, or by cap signaling. And this is called a distance control. So it is important to understand that these two characteristics are fundamental and are shaping the railway operational procedures. And now we come to the interlocking and traffic management subsystem. So what does it mean that in order to operate the trains, you have a system which is implemented on the infrastructure, on stations, and on the open line, which is the line between stations, and which is in very traditional approach based on the first of all the operational level, which is consisting of dispatchers responsible for entire line, and operators which are located at each station and are responsible for setting and allowing the trains to move from one station to another station. And this is done by means of interlocking. So interlocking as a system consists of operational control level, in other words, MMI interface to control the status of the system and to operate the system. Then interlocking level, which performs safety check of the operator's commands to secure the driveway for the train. And then the third level is element control level, which performs control and status monitoring of the field elements. And the field elements itself are located along the track, and they consist of switches or turnouts, signals, train location elements, and train protection elements. And the task of the operator is to arrange the train movement from a starting point to the target point by setting for it the driveway. How the driveway is being set. So it is important that any change of the location of the train is allowed only on the protected driveway. In order to meet this condition, the protection of the driveway consists of 7 steps described below. So the first of all, the interlocking system checks whether the driveway is free. So whether the track sections are free. Then, if it is free, the interlocking sets the movable elements into the right positions. So switches are set in the right positions. When it is done, the interlocking locks the route and provides the protection to the locked route by means of neighboring turnouts. And afterwards, when the route is locked, the driveway is ready, and the interlocking could give departure order by means of a signal, for example, to the train driver that the trip is allowed. During all the trip on this section of track, the interlocking maintains protection of the driveway and keep all elements locked. And only when the driveway is freed by the train, interlocking is releasing the protection, and the elements, the driveway section, could be used to set another route. So you see that the train movement is allowed only when all possible hazards are excluded. Before the movement is allowed, and also in the time when the movement is executed. And the traffic management system as operational interface provides to operator possibility to set the driveway, lock the driveway, and allow train movements in the part of the railway network which is in his responsibility. On the drawing below, you see a picture example of the TMS interface. So you see that the driveway or tracks are divided into the different sections. Each of the sections has its own number indicated in white color. The red sections are occupied. The sections in green are reserved for a specific train, and the number of this train occurs on the screen. Sections in white are not reserved, and the signals are as well represented as an arrows, and the color says about the either permissive aspect of the signal, green one, or red is the restrictive aspect of the signal. So operator can set routes for trains and follow up the train movement and as well temporarily put track sections out of service in case if any maintenance needed. The next subsystem is signaling and train protection. And this comes to the play when the driveway is set, for example, and the driving order shall be transmitted to the train driver. So this is called signaling. So the driving order by means of the signal is transmitted to the train driver. The classical or conventional solution considers that this is the optical signal. And such a driving order gives information on a few aspects. So first of all, that the protected or set and locked driveway is available. It gives information on the allowed driving speed, and it gives information on the aspect of the next signal. And according to this optical signal, the train driver operates the train and proceeds. So the train driver follows the driving orders. He drives the train according to the permitted speed. This is the function of the signaling. And when we look at the train protection, it comes to the play as an additional functionality which enforces a driver to note safety-related driving orders in a way that train protection influences or controls train independently from the train driver. For example, when the driver is passing the signal with the red aspect, the train protection executes emergency braking. So train protection monitors how the train driver is following the driving orders of the optical signaling and performs braking, automatic braking before the hazards, for example, signal with restrictive aspect, or follows the permitted speed, so reduces the speed in order to not overspeed. It is important to mention that the train protection as a system consists of trackside and train-side equipment. It means that there are elements or there is equipment which is located along the track, and as well the equipment which is located on board of the train. So what is important to understand that actions of the train driver are supervised by the train protection, and train protection triggers emergency braking in case of the human error. So in case of the error of the train driver. If we look in more detail at the types of train protection, there are two different types. One of them is called punctual train protection. The system checks the train speed only at the specific locations. So in the diagram on the left side, the speed would be then checked in point 1 and point 2 at the signal locations. And continuous train protection, this is the second type, checks the entire braking curve. So it checks the speed during entire trip of the train. And such type of train protection is implemented on the high-speed lines. And it is obvious that continuous train protection requires more complex and more costly train and trackside equipment. So please be aware that punctual and continuous train protection systems are two different systems, and the status of today's development is that most railway lines are equipped with both train protection systems due to the mixed traffic, so that you have fast passenger trains and relatively slow freight trains or regional trains, and that migration from one train protection system to another train protection system is a long-term process which could take several years. The next particular type of train protection, which I would like to explain in more detail, is ERTMS, European Railway Traffic Management System. And the idea behind ERTMS is that in European railways there is a lack of unified standards. So comparing with the automotive, where there are standards for variety systems for vehicles, in vehicles, where there is a compatible traffic signals, and comparing to the airline industry, where there are excellent interoperability, and the airplanes could go to any airport in the world. In railways, there is very low level of standardized systems. There is the mostly country specific systems, a big diversity of interlocking and train protection systems, which makes impossible for a train to go from one part of Europe to another. And due to the fact that this unified railway system was historically missing, the ERTMS has a function or role to become the unified system, to enable cross-border operation. And the main ideas of the ETCS or ERTMS is that it will bring trackside signaling into the driver cabin, provide information on the onboard display, and would reduce the complexity for a train driver when the train goes through different countries. So the information which is then displayed in the driver cabin shows the distance until the end of the movement authority, or the distance of the secured driveway, which is in this case 2.19 kilometers. It shows the target speed allowed, which is dynamically adjusted based on the available driveway. Then it shows current speed of the train, and it shows as well the target speed, which is in this case 0 at the end of moment authority. And by this means, ETCS reduces the complexity of the signaling and interpretation of the signaling from optical signals, and significantly decreases the risk of human error. Looking at the functional structure of ERTMS, we shall mention that the interlocking system, as it was described previously, remains, but the information on the available driveway is transferred from interlocking to the train via a radio system, and the onboard computer in the train calculates all the parameters for the train movement. So, for instance, train braking curve, permitted speed, train location, and distance to the danger point, or distance to the end of the driveway, which is set for the train. So ETCS level 2 ensures continuous train protection by means of the data transmission from interlocking, so from track side to the train. And now coming to the ancillary systems which are supporting or additional systems of CCS, I would like to stop on one of these systems, which is called point heating system, and this is installed on turnouts to melt the snow and ice on the movable parts of the turnout, as the driveway is set in advance by switching the turnout in left or right position. The prerequisite, or the switching itself, shall be secured as well in the winter, when the heating shall melt the snow and ice. And this is, for example, one ancillary system which is part of CCS. And other systems which I would like to mention are, for example, rolling stock health management system, which checks wheels and axles of the passing trains to avoid rolling stock accidents due to its failures. The other one system is road vehicle detection, which detects the vehicles in case if it fall down from the road overpass on the track, and thus could cause a collision and derailment of the train. And another system which is worth the mention is platform gates or platform access, which secures passengers on the regional station platforms from the high-speed trains which are passing by and not stopping at the platform. So thank you very much for participation, and you are welcome to ask any questions. I will go to the chat to check whether we have some questions. Please feel free to put your questions in the chat. So we have one question related to the different train protection systems which currently exist. So I would say that historically, due to the fact that railways were developed in early 20th century as the strategic infrastructure, that each country implemented its own railway systems. So there is like country-specific interlocking system and country-specific train protection system. And this is, for example, one of the reasons why currently, when Baltic states already for years are in the European Union, the railway system of Baltic states is and remains interoperable with the railway systems of Eastern countries, so Ukraine, Belarus, and Russia, Kazakhstan, and is not compatible with European countries. So this is, I mean, not only the CCS systems, but as well the track width, for example. Yes, there is another question from Oscars. What is the difference between CCS for high-speed line and for conventional line, which are currently in operation in Baltic states? The main difference is if we are comparing now CCS for Rail Baltica line, which will be ETCS level 2, with conventional lines, which are currently in operation in Baltic states. First of all, the difference is in speed. And due to the lower speeds of the existing railways, the train protection system is limited with, I would say, with 140 kilometers per hour. That's why for higher speeds, there is the need to implement the ETCS system. In other words, that there is a different system which is used currently for conventional railway lines in Baltics, comparing with the one which will be implemented for Rail Baltica. The next question is, I would say it, the question is which CCS subsystems will be implemented on Rail Baltica line, as said previously. So it will be ETCS level 2, which is automatic train protection system. The interlocking itself will be implemented based on EU links specification, which defines the interfaces between different parts of interlocking, so between interlocking and traffic management system, so the interface to operator, and then as well between interlocking and trackside elements, which will be in our case turnouts and axle counters. So axle counters fulfill the function of track clearance detection. And we will not have signals due to the fact that all information on the track vacancy and allowing the train movements will be depicted directly in the cabin of the train. So in Rail Baltica system, and which is one of the targets of ETCS level 2, you do not need signals along the line. All information is transmitted directly to the train. The next question is following from Niklas. Does current CCS allow direct passenger train movement between Baltic states on 15-20 millimeter track? For example, direct train Riga-Tartu. Yes, I mean, for instance, it allows, and this is one of the main challenges, I would say, when we modernize the 1520 infrastructure, which is currently interoperable. So the train could go from, for example, Riga to Estonia or to Lithuania. When we modernize the infrastructure in one country, it shall be as well considered that or how such a cross-border operation will take place in the future. And the idea of ETCS is that the standard or the system ensures that the interoperability is kept between countries. The next question from Fyodor. What kind of train radio system will be used at Rail Baltica infrastructure? There are two standards for radio system. One of them is the current in-force standard, which is specified in the EU regulations, which is called GSM-R. However, due to the fact that this is in practice 2G, so 2G system, which is quite old and doesn't used in public market anymore. So you know that we are talking now already about the 5G standard, which is 3 generations forward. That the current standardization work of institutions is considering that in year 2022, so next year, there will be a new standard based on 5G for railways, so which would be called FRMCS, or Future Railway Mobile Communication System, which is planned as a successor of GSM-R. What does it mean for existing railways using GSM-R? It means that they shall plan to migrate from GSM-R to this next generation standard. But for Rail Baltica, as we are so-called greenfield project, which will go in operation in the future, that we have the option, the possibility to introduce directly FRMCS standard and avoid the migration in the future. And the decision, of course, will be dependent on the readiness of the FRMCS standard, as as it first of all shall be technically prepared and available, and secondly, it shall be described, defined in European EU regulations as the mandatory standard for railways. So the next question is regarding the ancillary systems. Does the point machine monitoring system considered for RB? I'm not 100% sure what is meant by the point machine monitoring, but I assume that this is the system is meant which collects the parameters of the point machine. For example, current of point machine, position of point machine, and number of operations of point machine, for example, and collects this data to be used in maintenance purposes, for example. In this case, the answer is yes. Yes, the point or switch systems will be equipped with this monitoring system. I do not see any more questions. So thank you once again for joining. Thank you for your questions. And we have one more question for ancillary system. Just a second, I will go to the chat. Jiaming Huan for asks for ancillary system. We have many mountains and typhoons in Taiwan, and therefore the landslides cause risks to railway safety. Is there any landslide detection example in Europe? I believe yes. There are systems to detect the landslides or rock falls. For example, I know that conventional system is consisting of the wires, which are, in case of the fall, are broken, and this gives the signal to the interlocking that the gauge, track gauge, so this is the space used by the train vehicle, is intruded. Or, for instance, another modern way is to use the optic fiber sensing, which utilizes the optic fiber cables installed along the line and interprets the vibration sensed by optic fiber in the way that you could interpret the specific vibration as one or other activity besides or in the gauge. Yeah, I think then thank you for your interest and participation, and it was a pleasure to talk to you. Thank you very much, and see you in the next sessions. Thank you.